For those who might not know me, I'm Barry Stahl. I'm a solution architect and developer, and I work for Carvana. And I'm here to talk about patterns for building reliable systems. So some people might know me as the guy who maintains a list of his favorite physicists and favorite mathematicians, and that probably tells you everything you really need to know about me. But that said, I also like to talk about such a list. So I'm happy to argue about this. Please, on Twitter, I tweeted about it. My Twitter handle is on every slide, BS Stall. And feel free to tweet me about it and tell me where I messed up. As I said, I work for Carvana and we are hiring. So sorry about the horrible link, but this slide deck is available online, and there's an actual clickable link on the resource slide at the end. So if you're looking right now, we're hiring in all areas of technology, and it's an amazing place to work. I highly recommend it. So come hang out with us. And there's several of us on this call today from Carvana, so feel free to ping us and ask us about it if you're interested. All right. I'm also an open source contributor, so I have a number of open source projects that I contribute to. None of them are particularly relevant to this talk, so I'm not really going to go into them in detail, but they're all linked here in the presentation slides. And I'm one of the founders of Arizona Give Camp. So Give Camp, in case you're not familiar with it, is a weekend event where we put a bunch of software creators in a room with a bunch of local nonprofit organizations, and we code for them. And you know, a lot of times we try to make it the ones that really need our help, that wouldn't be able to afford it otherwise. So we can do some amazing things for them. And as our good friend Rob Richardson likes to say, sleep is optional, caffeine is provided. All right. So we're going to talk about reliable systems. And so to illustrate this, I'm going to use this example pretty much throughout the presentation. We'll add on to it at the end a little bit, but our example is going to be a service that makes two changes to the system state. It sends an email message and it writes the results to a database. Pretty straightforward. Might look something like this, where we have the browser, user using the browser, calling a web service, and it does these two things. Pretty simple. Might look in code something like this. Now I've abstracted away all the complexity, but you can trust me here that the comments are true, that under the covers, we are actually doing proper error trapping. So we're handling errors and we're retrying an appropriate number of times for each of these. So this is decent code. This is reasonably well done. It traps for its errors. It tries to do the work. And it has these two different things that it needs to do. All right. So this code is good. Like I said, we've all probably written code like this. I know I have, but there is a problem with it. And to illustrate that problem and how these the different techniques we're going to be talking about today are affected, what I'm going to use is charts kind of like this, where along the top here at this point is what happens? What are the circumstances? Whether in this case, all tasks succeed, task A fails, or task A succeeds but B fails. Now, with two tasks and two possible states, failed and succeeded for each one, that would actually result in 4 different possible states. But in this case, since if the email fails, that's going to throw up an exception. We're never going to actually do the database update. So that state is not possible to get to. So we have 3 possible states that we need to consider. So what happens when these different states occur? Obviously, if all tasks succeed, we're fine. That's the happy path, all is good. But if task A fails, nothing happens. And that's actually probably okay, or it could be okay, in the sense that we're at least leaving the system in a known state. We didn't do anything. But if we were to come back and retry later, and that retry were successful, we'd still be fine. So I have this as a smiley face, just not a green go smiley face, because we're actually okay here, but not okay in a way that actually worked at this point. The real danger is—
I have a question though.
Well, that's not allowed. Oh, okay.
We're making some assumptions here. If task A fails in the process of sending the message, then it probably didn't go. If task A failed in the process of deserializing the results after the message already left, then we'd yield a different result.
We might, and we'll talk about that kind of thing as we go through. I've kind of simplified this at this point. Actually, not really so much, because for SMTP is pretty straightforward. But you're right, you do have to consider that if you get an error, that doesn't necessarily mean it wasn't done. And yes, and we will deal with that. Thank you for pointing that out, Rob. So task A fails, we did nothing, but we're in a known state, and we could come back later and try it out. Task A succeeds, but B fails, and this is sort of what you were talking about, in that the email has been sent, but the database didn't update, and we didn't know about it. Or we threw up an exception, and but we still sent the email. So this is not a good state to be in. This is an unknown state. We left the system in a state that we don't really know for certain where it is or what happened. So we need to—
I'd say less that it's unknown and more that we're assuming the wrong answer. We're assuming nothing happened.
Depends on how we handle it upstream. Yes, it could be that we've assumed that nothing happened because we got an error. It could be that if we throw two different types of exceptions here, we could know what happened, which step failed. But we at that point we have to know something about the internals of this method, which also is not a great idea. So there's, again, a number of different ways this could end up presenting to us.
Good call. We could have a known unknown, and we could have an unknown unknown.
Right. But all of them are bad. Just some are worse than others.
Exactly. If we assumed that nothing happened and we retried the entire process, 19 emails later, our customer would go, "Can you knock it off?"
Hey, what's going on here? Yep, and we're going to see that coming up here. All right, so what else could we do? How can we make this better? One thing that that comes up commonly when we're talking about this is wrapping it in a database transaction. So in this case, because we're using SQL Server here, we can actually start a transaction using this repository, then send the email, and then if the email sends properly, if we don't get an exception there, we can then commit that. And that feels like it should make this more reliable, right? Because, I mean, what can really happen on commit, right? You've already established that you've got a connection to the database. So it feels logical that this would improve reliability. I think it's pretty obvious from the way I'm saying it right now that it doesn't really, but let's look at why. So we now have 4 states that we have to consider, because we actually have 3 tasks, all sort of dependent on each other, in the sense that this second one won't run if the first one fails, the third one won't run if the second one fails. So we just have 4 states, but they're really basically the same as the previous ones. It's just that we've split this middle one out into 2. If all tasks succeed, we're still good. But if A fails, that's the begin update. Or if the begin update succeeds, but the send fails, assuming it fails completely, we are in a known state, but nothing happened. because we roll back the database update when the email send failed. But we're still in the same situation if the commit fails, right? We're still in the same situation. If we try and commit it and that fails, we've still sent the email. We'll roll back the database transaction, but the email got sent. There's no way to roll that back. And here's the real concern with that, and that is that reliability for most dependencies is not based on the number of transactions. It's actually based on the time spent doing the work. So the longer an operation takes, the greater its chance of failure. And it really isn't like, you would think doing 2 operations has twice the chance of failure. That's not the case. If your single operation takes longer than those 2 operations, that 1 operation actually has a greater chance of failure than the 2 operations. So you're actually better off breaking up transactions. And here's sort of an illustration of it. These are the sequence diagrams for the 2 examples we've used so far. So in the first one, we send the email and then we do the database update. So the critical portion for the database is right here. In this one, we're starting the transaction, doing our email send, and then committing the transaction. And of course, this is not to scale. Transactions are really slow. So it may very well be that we're spending some multiple amount of time in this transaction than we would be if we were just doing it here. So my feeling is that we're actually reducing reliability here. The thing to remember is that transactions are about data integrity. They're not about reliability. You can't get reliability, or you're not going to get reliability from adding transactions. What you're going to get is data consistency. Does that make sense? All right. So what else can we do? Well, the only other thing that I'm comfortable talking about at this point is that we can retry at the client. So, and this is usually a bad idea to do if it's actually at the customer end. But whatever the client is, whatever the source of the trigger, whatever the trigger is for this action, if it fails, we could retry it. So what I've done here is I put the 4 different ways to handle those 2 possible errors. And what we end up with is 2 options for each. We can either continue if it fails, ignoring the failure, or we can, what I'm calling, roll back. And roll back in this case means throw an exception. And then we have 4 possibilities along the left side here of whether the task succeeded or failed. They can both fail, they can both succeed, or one or the other can succeed or fail. Obviously, we're in the happy path where both tasks succeed, we're all good. It's in all the other paths that we have some concern. So let's look at each of these possible implementations, because that's what we have along the top are the different implementations. So let's look at these implementations and see what they do for us. So if we were to just continue on either task failing, I call that the ignore errors implementation. That's my name for it. In that case, we're good if both tasks succeed. Happy path is fine. But if A succeeds and B fails, we're going to have done A, but not done B. If A fails, but B succeeds, well, that depends on if it's even possible to do that. If B, for example, if it was a database update, but that needed a response from A before it could do that, if it's dependent on it, then we can't even get to that, and it's just not even a valid state. If it is, what we probably end up with is that we have this half circle again, but it's reversed. So B, we did B, but we didn't do A. So we updated our database, but we never sent the email. And then, of course, if both tasks fail, we've done nothing. and we've just ignored it, but we haven't thrown up an error, so nobody knows we've done that. This is far too common, I would say, in the world of software development. And I think it's something we've all done. And I also think it's the thing that we almost always start with. I'm thinking that, you know, it's pretty common to say, all right, I'm going to implement it. I'm going to ignore the errors for now, just so I can get it working. I can see it working. And then, of course, we go back and fix it, right? This is just for testing, right? Right? So, so that's the ignore errors implementation. Obviously, that's not a good idea to put that into production. Unfortunately, I think it does get put into production a lot. Every company I've ever been at, I've seen implementations of this. So what else can we do? Well, option 2 is what I call the logging implementation. In this case, we roll back if A fails, but we continue if B fails. So in this case, A is our important task and B is less important. And in this case, if A succeeds but B fails, well, we've done A but not B. If A fails but B succeeds, well, I've got a smiley face there because what's going to happen is we're going to throw up an error on A. We're going to roll that back, and then we're going to retry that. And since we haven't accomplished anything, we haven't actually done any work yet, we're okay here because hopefully the retry later will cause it to succeed. Hopefully that's a transient error. And then, of course, if both tasks fail, again, because we roll back on task A, we roll it back and we retry later and we're good. So I call this the logging implementation because what this gives us is fairly reliable code for task A, but far less reliability for task B. So that's good if you have a task B that is not so important, for example, logging, right? We don't want to throw an error up to the customer because our logging fails. We want to alert on it. We want to know about it. We don't want to find out that our logging is broken when we actually have some other real problem. But we don't want to cause an error to the customers for this. So for a situation like this, this may be okay. What other options are there? Continue if A fails, roll back if B fails. Now we start to get weird. With this one, if A succeeds but B fails, we're going to roll back because B failed, but A succeeded. So we sent our email. We're going to roll back. We're going to try again later. And this is where the 17 emails that Rob was talking about earlier come in. We're going to double tap this thing. Every time we retry this, we're going to send off that email. Likewise, we're in a similar situation with this one as we were over here. If B is dependent on A, it can't succeed without A. So we're in an impossible state here. But if it isn't dependent on A, then what we've got is a situation where we've done half of it, right? We've, let's see, continue if A fails, roll back if B fails. B has succeeded, A failed, so we didn't do A. We didn't send the email. We did update the database or what have you, but we don't retry. So we only did half of our process. But of course, if both tests fail, we're okay there. I called this the indeterminate implementation because this is the one where it's really hard to know, and it's very use case dependent, what actually happened. And it's very dependent on when the error occurred. So if you're talking about a hardware failure here, that could have occurred at any point in the process, where it manifests can be really important, and you can end up with really strange, very difficult to troubleshoot errors. We'll talk more about that a little later on. So obviously this is not a recommended implementation. Finally, we have what I've called the idempotence implementation. We'll talk more about idempotence in a moment. This one we're okay under any circumstance except if A succeeds but B fails. And then the only problem with that is that we're going to end up doing A twice because we're rolling back on either task failing. Everything else is going to cause nothing to happen. We're going to roll back and we're going to try again. But if A succeeds, we're going to roll back on B. A is going to get done twice. So there is one time where this is appropriate, and that is when task A is idempotent, which of course email is not. Well, maybe it is. We can talk about it. Let's talk about what idempotence means for a second first. Idempotence is the ability to execute a task some number of times greater than one, and have the state of the system be the same after the nth time as it would be after the first time. So the canonical example from Wikipedia is these European trains start and stop buttons. If the train is not running and you hit the start button, it's going to start. If you hit the start button again, it's not going to do anything else. It's not going to change the state of the system. You can hit that start button as many times as you want, and it's not going to affect the state of the system once the system is running. So one time is the same as executing it n times. That's idempotence. There's several other things that are idempotent, but the one that I really find very interesting and useful are database upserts. If you do a database upsert like this, where you're passing it in 3 values, an ID, in this case, an email address, and some content. The first time you send it in, if it doesn't have that row, it's going to create that row. So it's going to do the insert. If it does have that row, so you've said now you're putting it in there a second time, it's going to do the update, but it's going to do the update with the same data. So you can execute this procedure as many times as you want, and as long as you send it the same inputs, it's going to result in the same state of the system. That could end up being very useful. All right, so let's go back to our chart here. So this is useful if we have idempotent solutions. Now, I said email is not idempotent because you could end up sending multiple emails. You will send out multiple emails, right? If you're just using the SMTP server. But there may be a way to create a service that can check that and see if you're sending the same data and then not if you've already sent it. So that's one possibility. That has other problems that go along with it that are reliability issues that we'd have to be concerned about. Another situation is that maybe it's an internal email that's only sent to support text or something like that. And in those circumstances, they say, you know what, it doesn't matter if we get multiple emails because we can be the idempotent solution. We can understand that occasionally we will get duplicate emails and we can hit the delete button and the state of the system is the same. So idempotence itself is, you're going to have to decide if your solution is acceptable from an idempotence perspective. All right. So
I can see a potential 2 generals problem though. So now we have a system that is able to determine if this email has been sent, but inside said system, it needs to do 2 things. It needs to send the email and keep track of which emails have been sent. And now we've got the same problem over there instead of over here.
Yep, exactly. That was what I was referring to. And we'll actually drill into that a little bit as we go forward. We'll talk about 2 generals a little bit and briefly anyways, and talk about the problems that, because we're going to have some of those problems no matter what we do. So we'll talk about how that figures in. So here's the big concern, the big reason what this all tells us is that we can only make 2 changes to the system state in a single execution context if either the first change is idempotent or the second change is made unreliably, like our logging solution. It is not possible, this is my my interpretation of all this. It is not possible to reliably make more than one change in a single execution context. It is not possible to do. So, reliability, we don't have it. Well, we can get good enough, but we can never get 100% reliability. So that's something to keep in mind. Something else to keep in mind is that what we're going to want to do is make sure we do as much as we can to keep our reliability as high as possible. And we'll talk about ways to go about doing that. So let's define this thing a little bit. I've been talking about doing two things at once. And the reason for that is because there is this anti-pattern that has been defined that is called the dual writes anti-pattern. So let's define what it means to do a dual write. A dual write is any attempt to make more than one reliable change to the state of a system in a single invocation. Now, there's some words in here that probably need further definition. So let's drill into those just a little bit. I said it's an attempt to make more than one reliable change to the state of a system. In this case, what I've defined reliability as 4 nines. Okay. My heuristic for reliability is that 3 nines is basically not reliable. That's what we need. That's what we use things like logging. Logging as 3 nines. Most of our production stuff, most of our dependencies, most of the cloud services that we use are going to be 4 nines. That's what the reliability guarantees they're going to give us are. Very rarely will we ever get 5 nines reliability, either by ourselves or from a cloud service. 5 nines, to get to 5 nines, I can't think of anything other than basically a static service that takes data, doesn't have any dependencies, does a calculation and just returns the value. That's something that might be a 5 nines reliability service. Anything that uses a dependency can have its maximum reliability as the reliability of that dependency, and it's always going to be less than that because we've included our own lack of reliability on top of it, plus the network between them and all of the other things that could possibly go wrong. So that's my definition of reliability here. So you can't.
And if we have multiple dependencies, our reliability gets worse because it's not the difference between the two systems or the best of the two systems, or even better, it's actually exponentially worse than the two systems combined.
I'm not sure if exponentially is the right term, but yes, it does get it, at least multiplicatively.
Yeah, multiplicatively, that's the right word.
Yes, that is correct. So the more we do, the less our reliability, the less reliable we are. That's what I'm looking for. So don't do dual writes. We'll talk more about that. So by change in this case, what I mean is an atomic modification. So we can make as many changes as we want to the database as long as it's atomic, recognizing that transactions themselves slow the process down. So, but the key is, because it's an atomic transaction and will fail or succeed together, we're only doing one thing. Similarly, for something like an API call or delivering a message to a reliable messaging service like Kafka or RabbitMQ or what have you, or sending an update to a log. And then this is the interesting one. This one is per invocation. So this is really important. I define this an invocation as an automated response to a signal. So the simplest example of that is a web service, web method, right? So we get a message at a web method, we execute something, and then we either throw back an error or an HTTP response code. Now, it's always an HTTP response code, but we respond with either an error or a success. Same thing with a reliable message. We get a message, we do something with it, we commit it. A single invocation. And that's critical because the more we try and do within a single invocation, that invocation is the unit. It's really hard to describe at this point, but this is the thing that encapsulates the entire process. I think that'll be a little clearer as we go forward here. All right. And the reason I find these so troubling is that they really are the most difficult of types of errors. They can be, are you familiar with the term Heisenbug? It's there until you look at it and then it's not there anymore. You could really end up with bugs that are really, really hard to find or really hard to replicate. You can end up with all different kinds of situations. So it's hard to profile what it looks like because a lot of times it never happens twice. I mean, if you're talking about hardware failures, for example, or network failures, they never happen at the same. You can't predict when they're going to happen. You can't say, I'm most likely to have a hardware failure at this time. It doesn't, you can't predict that. So there's no way to know what it's going to look like, how it's going to present itself. And it's very difficult to support it. It's difficult to identify when they even occur. So you may not know if an error happened. Even if you do, you can have a tough time replicating it, certainly. How do you replicate a hardware failure? And it can be difficult to remediate. It's always a one-off solution to fix it, even if you can find out what happened and what to do to fix it. You're writing a database update script that's a one-off script or something like that because you're doing two things at once already. Those two things, one of them worked, one of them didn't. You can't just use your existing code to fix the problem. So you've always got to create these little one-off solutions to solve these problems. So these are problems that we really want to avoid. And these are problems that cause us to have to give up our nights and weekends when we're on call, right? When we're doing the support for our applications. So really good idea to avoid these whenever possible. So how do we avoid them? Well, the key to it is to keep it separate. If we keep it separate, we keep it safer. So the rest of this talk is going to be looking at different ways where we can separate these things, where we can make it so instead of doing 2 or 3 or 4 things all in one, we're going to look at ways to separate them and say we're going to handle one thing at a time, so that even if when failures do occur, we're left in a known state. So we're going to look at several different patterns for doing that. And we're going to start by looking at the transactional outbox pattern. So the goal of the transactional outbox pattern is to reliably update a data store and then trigger an additional action from that update. So we make a change to the state that's stored in the database, as well as, and this is an atomic write, so we make a single write that does 2 things. It makes a change to the state, and it writes a command out to execute a secondary process. That's our outbox. So we have our state, we might have a state table for that, and we have an outbox table that is a list of commands that need to be executed downstream. Let's take a look at some code and see what that might look like. I know Rob's all excited now. We get to look at code. Code. All right. So I should point out that all of this code is available on GitHub. I can actually show you that. Here it is. So all of this code is here, and it is exactly as you'll be seeing it. And there's a link to it at the end of the presentation, so you'll be able to get to that from there as well. If you didn't capture it there. So I've got three different solutions here. This first one is an outbox solution. Now I'm gonna spend a little more time on this one than I will on the other ones, because I'm going to go through the common elements of it here first. These common elements are in all three of our solutions. And this is our domain information. So we're going to have things like, thank you, Rob. We're going to have our request object. So our system in this case is going to allow customers, users, whatever, to make requests of us. So it's going to ask us to do a thing, our company. Okay. So each request gets an ID, has the email of the customer, and a description of what they need us to do. Super simple example. We're going to be sending them emails, so I have some extensions in here that are just common extensions for getting the email subject and body based on the information in the request. And then we've got two abstractions here. We have a thing that can issue the request. So this is our sort of our ingress, the thing that knows how to make those requests and write them into our system. And then the thing that knows how to send a message to the customer about it. And then the other thing we have here is an email client that just knows how to send that message. So that's the thing that implements this I send messages interface. These are all the common elements. And all that code, like I said, is in GitHub. Of course, you won't be able to run it because all my secrets are in secret management, so you can't see those. You'll have to put your own in. All right. So let's look at the code for this outbox example. We're going to start with the request service. This is our ingress. So we have some logging, some configuration, we have our dependencies, all right? And the primary dependency is the thing that issues requests, our I issue requests service. And so all we're gonna do here is we're gonna take the arguments from the command line, create a new request out of it. So the first argument is the customer email. The second argument is the description. We're doing this massive validation right here to make sure that all of our data is valid and will not cause problems in our system. That there's no SQL injection attacks in there and all that kind of stuff. That's all handled right here in this one to do. And then we call the service an issue request. Let's go take a quick look at that. And in this service, I put in here a comment that I've put the logic for the email here in the ingress. So what we're doing is we're actually going to write both tables out here. We're going to write out information about the state of the request. Basically, we're going to write the request out to one table, and we're going to write all the information we need out to the other table, the outbox table. I could have done it where I just only wrote the information once and just linked back. This is how I chose to do it in this scenario. If we were doing a dual write, it would be right here to begin with. So we take that information or do some logging, and then we'll call our repository save request. And this pattern is going to be repeated throughout these services. And in this case, what we've got is a SQL Server repository. So you can see we've got two, let's move this over here a little bit. We've got two insert statements. We're going to insert into TBL requests and into TBL messages. TBL requests, that's our state table. TBL messages, that's our outbox table. And you notice there's a sent value on the outbox table, and we're going to set that to 0 when we first start. And then these writes are all done here within this transaction. So here's where we start the transaction. We issue the two requests. So we execute the insert into TBL requests. We execute the insert into the TBL message. and then we commit our transaction and we're done. So all we've done is we've put data into SQL Server, we've written it into 2 different tables, and the outbox table has a flag on it that tells us whether it's sent or not. Sent equals false is how we insert it. All right. So that's happening. And as we do that, while that's happening, we're going to have another service running. And this service is going to be running in the background. This is our email service. So this service is actually watching for those messages going into the database. It's going to be polling the database. And it's looking for those messages that haven't been sent yet. And yes, Rob, we have to be very careful with this, that if we scale this out to multiple clients, we have to be super careful that we don't get race conditions, that we lock our rows properly so we don't have multiple things trying to get the same record at a time. Super careful for that. This is a very simple implementation if it's done with only one instance of the service. It gets much more complicated if it's scaled out. And we'll talk a little more about that too. So the key to this one is our processing engine. So let's take a quick look at that. So when this starts, what it's doing is it's waiting, it's checking to make sure the cancellation token hasn't been canceled. So it'll run until that token gets canceled. We do a quick delay so we avoid a tight loop. And then we call the repo, or the database repository that says, give me all the unsent messages, or actually, sorry, give me an unsent message. I only asked for the first one in this query. And it's going to sit there. It's going to either give me back a message if there is one that's unsent, or it's going to give me back a null if there isn't one. And so I've got a debug log here that says no messages are queued. Since that's logged as a debug thing, normally in production we wouldn't see it, but I've got it turned on right now, so we'll actually see it in our logs. So if there's no message, we're just going to get that, and it's just going to spin and delay and try again. However, if there is a message in there that hasn't been sent yet, this is where we do a send on the email client, which we looked at earlier. So it's going to send our email using the information from that outbox table. And then it's going to go into the repo and update that the message was sent. We're sending an email and we're doing an update. Doesn't that seem like a dual write? It does kind of, doesn't it? It's because it is. And we'll talk about why that's a problem and not a problem. So let's see this in action here. I'm just going to run the email service. I've got the email service set as the startup project. I'm going to run that and bring the log over to the proper screen as soon as it actually spins up. There we go. I spun up these demos, but it was like, 2 hours ago. So, all right, so we're starting message processing over here. And now we're in our outbox. So here is the request service for the outbox pattern, and I built this earlier. So let's create a request, and this request is going to come from Rob at definitelynotrobrich.org. And he's saying his request is please clean up after the meeting. All right, cool. So let's create this request. Boom. We issue the request, it writes it out to the database, and of course, then you can see that the service picks that up, finds it, and goes and sends the email. And now if I have my email client up, oh, there's our email. Ooh. Your request with tracking ID was received and will be processed as soon as possible. Cool. We can also look at the database. I think I have in the code, I have Well, let me show you a couple of things here, actually. I've got, and you can't see it in here. One thing you can see is I've got for each of these patterns, I've got a sequence diagram in the code that you can look at. And in fact, if you have the Plant UML extensions on in Visual Studio or in Visual Studio Code, you can actually see the sequence. And I think what you're going to see is that the sequences for all of these first three patterns are nearly identical. They're just different implementations, different ways of doing very, very similar things. And Joe, we're going to talk about message queues, not the next one, but the one after that. Okay. All right. The other thing in here that you can't see it in, it's not in the Visual Studio solution, but it is in the code, is that there's a notebook, a SQL notebook that will show you the database shot, assuming you have it connected to the same database that you connected this to. Is there any questions on this? Everybody's muted, so you know it's hard to know if it's silence because there's nothing to, no questions or silence.
I like it. It looks gorgeous. Is this Visual Studio 2022?
No, I am not that brave yet on my, this is my production machine. I'm not that brave to install 2022, although I do believe it is a preview version of 2019. So
yeah, it's a preview. It says it in the right-hand corner.
Yeah. Yep.
But they're side-by-side installs, so shouldn't have to worry about it in theory.
Yeah, I may, while I'm traveling next week, I may install the 2022 on my laptop, but we'll see.
Do it over the plain Wi-Fi. Everyone will love you for it.
What could be better, right? No, I won't even finish unless plain Wi-Fi's have gotten a lot better since I last used them. They've had a year and a half, right? So who knows? All right. Let's get back to the presentation here. All right. So outbox pattern. The advantages of it is it allows us to persist very quickly. So the very first thing we do, we get data. The first thing we do, get it to disk, get it safe. And then after that, we can do other things. It does capture every update. Not all of these patterns that we're going to look at today will capture every single change. Some of them will only give you the current state based on a, on a time loop, timing loop. But this one will give you all of them. And it's pretty familiar tech to most of us. SQL servers, we have it, we know how to use it. So it's a common pattern, and it's a good way of doing things. It does have some disadvantages. I didn't list the fact that SQL Server is not really great at handling large blobs, but that is also an issue. But it can be very hard to scale. We talked about earlier, if you're trying to extend and add additional clients to scale this out, you're going to have to do work in here to make sure that you do proper row locking and they handle each other very well. Other implementations, other patterns do a better job of this, and we'll see that in the next examples. It's also harder to fan out in the sense that if I end up, right now you can do this one thing, you can send the email. But if it also turns out that, based on that same trigger, I don't want to just send an email, I want to do something else now as well. I probably have to write a new outbox table or maybe a new flag on that existing outbox table. I don't really like to update, I don't like to change tables. So there's different ways you can do it, but it's not something that you can just kind of automatically make fan out or make scale. You have to do work to make that happen. It's also using the database as a queue. We have queuing technology. Do we really want to use a database that really isn't designed for that purpose as a queue when we have queues available, as Joe pointed out? It also adds some weight to the persistence. I'll talk about this a number of times today. If somebody gives us some data, we want to get that persisted as quickly as possible and as safely as possible. The very first thing, with as minimal ceremony and as minimal risk as possible, get that to disk, get it safe. Well, as we talked about earlier, we're now adding a transaction to this, and we're going to write another row at the same time. And that's going to increase the risk of failure of that initial transaction. So it's going to make it more likely that we are going to fail that initial write. Now, we're going to leave ourselves in a known state if we do, because it's in a transaction. If we fail, it's going to bump back out and hopefully retry. And we're going to leave ourselves in a state where nothing has been done. So that's not the worst case scenario. But still, the best pattern is get it to disk as quickly and as safely as we can. And then finally, as we discussed, this is really important, and this is an issue with all of these first three patterns we're going to talk about today. And that is, we are still susceptible to errors on commit. We are still doing two things. There's no way to avoid doing that second thing. We just have to absolutely minimize as much as we can that second thing. We have to minimize as much as possible. The thing about this is, if we were to try and do two things at once, what we'd really be doing is three things at once. If we were sending an email and doing a database update, and then we had to commit or what have you, if we're, on all, depending on how we do these patterns, we'd actually end up doing three things. So it's really, we're going from 3 writes down to 2. But we still want to make sure we're aware of that we can still be susceptible to errors on commit. Does everybody understand or have a general idea of this pattern? I recognize you're probably going to need to go and actually look at the code yourself if you're really interested in drilling into it. Or are there any questions on this pattern at this point?
I really like this. As you were talking about, maybe we could use a queue. That would introduce a second dependency. And now we have the two generals problem again of, well, what if this database write works and that one doesn't?
Well, I'm going to show you how to do it right later.
Yeah, so I think the outbox pattern is interesting because you're creating that database transaction to ensure that both things either succeed or fail. That atomic piece is really cool.
Yeah. And it only gets better from here. Watch this. Oops. He says as he fumbles for the button. Let's talk about change data capture. This is another way of doing very, very similar things. And in fact, you'll notice I said the goal here is to reliably update a data store and trigger an additional action. That might sound really familiar because that's also the exact goal of the outbox pattern. The difference is, this is a single write that makes an update to the database. And then we use the database log to take the secondary action. So instead of us having to write another record to the database that triggers the downstream action, the databases themselves, they're all distributed databases these days. Oops. All our databases are distributed. They can all do log shipping for replication. They're all based on logs. So the fact is, we can use that log, or it can do it for us. We don't actually even have to do it. The database will take care of it for us. We can use that log to trigger the secondary action, and we don't have to do that work ourselves. Let's see what that looks like. And what we're going to do, we're going to use Cosmos DB to trigger this one. A lot of databases do, or at least a number of databases do, CDC or CDC-like action. Cosmos is the one that I'm most comfortable with. SQL Server will do this, but only certain versions of SQL Server. If you're using the Azure SQL instances, those do not today support change data capture. Cosmos does. So let's look at an implementation here in Cosmos. And if we look at the diagram, you can see it is almost identical to before. We're still going to have the request service. That's going to be our ingress, and it's going to push a message instead of now into SQL Server. It's going to push a message into Cosmos. And then we're going to have a service that's looping. And in this case, the change document is going to come down to us. And we're going to send the email based on that. So let's look at that code. Here's our ingress, our request service. And again, we're doing all the same things. We're getting the arguments from the command line. We're calling into the issue request. We're using the save request on our repo, on our repository here. But of course, this repository is now a Cosmos repository, and it gets a Cosmos client injected into it. And the key to this is this create item async right here. So we get a Cosmos, get a container off the client. We use the create item async method to write our request data that we got off the method signature here. We write that document into the database. And then we're done here at this point. So what we're doing is we're creating a document for each of these requests in our Cosmos container. When that document gets created, then we're going to have our email service spinning and monitoring for that. Now this one gets a little more complex, but not that much. I'm using the host processing from ASP.NET, I guess. And what we're going to do here, we have a little more configuration. We have to configure the Cosmos client. And then we're going to use this Cosmos change monitor here. This is provided by the Cosmos SDK. So let's go into the, well, it's going to use the thing that's provided by the Cosmos SDK. So we're still injecting our Cosmos client. Here's where we actually get the change feed processor. So when this is executed, when this service starts up, the first thing it does is it calls on the Cosmos client to get a change feed processor. This is part of the SDK for Cosmos. And then what we give it in there, among other things, is a reference to this process message async method, which you can see right below it here. So what happens is whenever a document is updated in Cosmos, in this Cosmos container, the container we're monitoring, and that's part of what the configuration is, it tells it which container we're monitoring. Whenever a document gets added or updated, this process message async is called with a read-only collection of the document. It's actually a read-only collection of multiple documents. You can have multiple documents. I usually configure it to only send me one at a time, but for throughput, you can increase that. That, of course, hurts reliability, so I don't tend to do that. Premature optimization, in my opinion. So what I'm going to get here is a collection that contains one document, and that document is going to be the document that we stored in Cosmos. And so we're just going to take that and we're going to call our message handler process async, which is going to do the get the email subject to body, create an email message, and send it. So we store a document in Cosmos. That document is then uses the change feed, the change log, pushes it out onto the change feed, and it monitors all where we are. So Cosmos manages a lot of the details of this for us. And it will push that document down to us into anything that's monitoring that container and allow us to take actions that are separate from the initial push. So we store the data quickly, get it out to disk as safely as possible, and then respond to the change messages in a separate service. Let's see that happen here. So I'm going to run the email service again. and this is the Cosmos email service. And we're going to jump over to our CDC request service. And there we go. We can see here is some information about, we're monitoring a container called requests. And we have an instance and a processor ID and an instance ID. And we'll talk about what these are used for here momentarily. Let me show you. We're going to now create a message from Robert at sonotrodrich.org. And he's saying his request is to please bring 7-Up to the meeting with you. All right, so everybody's got their 7-Up for Rob. Let's write that document out to Cosmos DB. And then, of course, it's going to be super slow, but what you can see is now we've got that message has been pushed down to us, and we're able to go and create our email. And again, now we'll have in our email, can I change tabs? I can without having to go into, and there we go. Now we got another email here. All right. Everybody cool with this so far? I like this pattern a lot. I like this better than the outbox pattern. I feel like this allows us to focus on the things that are important to us without having to deal with a lot of the implementation detail. And some of the advantages are really make it really obvious here in the sense that, well, just like with the outbox, we can persist it quickly. But unlike the outbox, these are very easy to scale and to fan out. So if I need to scale this service, all I have to do is spin up another instance with the same group ID. And what Cosmos is going to do is it's going to see that there's another consumer of messages from that group ID, and it's going to automatically rebalance and give some partitions to this client, some partitions to this client, and it will do it based on the partitions. So that means that within a partition, within that the keys that you give it, it will still maintain order within that partition. So if, for example, if your partition key is a customer ID, your messages, all your messages for that customer ID will come in order, even if you have multiple clients going. Likewise, it's really easy to fan out because all you have to do is spin up new clients with a different consumer group, with a different group ID, and that will create an entirely new group of consumers, and that will get all of the messages. So if you need to create an additional action, you know what, we already send emails, but now based on that same document update, we also want to call billing or whatever. We just spin up a new group of consumers for it, and Cosmos takes care of all the implementation details for us. It's a really, really awesome pattern, and it works amazingly well. There are two disadvantages here, though. This is the pattern where we are not guaranteed to capture every update. So unlike the outbox pattern where we knew everything we write into that outbox is going to get, we're going to get a message for that. In this case, if we make multiple writes during the time that we're polling, or if our client is down for a while, and during that time we make multiple writes to the same document, we're only going to get that document once. We will get it. We'll see that a change has occurred to that document, but we won't know if 5 changes were made or just one or whatever. We'll only get one update. We'll get the current state of that document when we come back up and start processing messages. So if you need to have every change, if you need to know that you need to see every change that occurred, this is probably not the right pattern, at least not with Cosmos. Other implementations may be different. And again, we are still susceptible to errors on commit. We still have to commit those messages. I didn't show you that in the code, but you will see it in the code that those messages are committed back to the database. And so when we consume them, if we don't throw an error, actually, that's why I didn't show you it there, because if you don't throw an error during the message processing within Cosmos, it will automatically commit it for you. If you do throw a message, it'll automatically throw an exception, it'll automatically roll back. So we could still have successful processing and then have the commit have an error, and we could end up getting the message again. All right. Finally, let's talk about streaming. I could have also called this reliable messaging, and that might have been a little more accurate. It's hard to say. But we're going to be talking about using reliable messaging services like RabbitMQ. In fact, we're going to do our work in Cosmos, in Kafka. But really, any queuing service will work for this. And in this case, we're going to make a single atomic write, but instead of it writing to a database, it's going to write to a message stream like Kafka or service bus topics or what have you. And then this stream is what's used to trigger downstream actions. So let's see that in operation. There we go. So again, here's our sequence diagram. And again, almost identical. This time we're dealing with a queue rather than a database, but same pattern from request service to our data store, and then subscription from the email service to send the email. So ingress. Same as before, grab the request and then issue it. Our repository is a save request again. This one is a Kafka repository. And so in this case, what we do is we construct a message with a key, and the value is a serialized, is a JSON serialization of our request object. We create a producer, a message producer for Kafka, and we use that to produce the message. And then I immediately flush that out. The Kafka SDK will also help you by batching things up for you. And so I immediately flush it out so it gets committed as quickly and as safely as possible. And then this SDK is kind of nice in that it gives us, we can actually tell it when we produce the message, we can give it a reference to a delivery handler, which will get a report on the delivery. So this will give us information about the partition and offsets and stuff that, and it also I have it showing us the message that gets, the value of the message that gets put in there. So we should be able to see that. So that'll push a message into Kafka. And then here is our consumer. This is our email service that now has to, we have to do some Kafka configuration stuff here like we did on the other. But then we have our Kafka change monitor. And that's what actually is watching for changes. And this one, we get a consumer builder. And once we build the consumer, we subscribe to those messages. And what that's going to do here is that's actually going to call consume on the consumer, which is actually a blocking operation. So in this case, what it's going to do is it's going to sit there and wait until one of two things happens. Either this token gets canceled or it gets a message. So that means that once I get here, either it's going to have been canceled or we're going to have a message here. So if we have a message here, we process it. If not, we bail out of our loop and exit the program. So processing the message here is just exactly what you'd expect. We deserialize that message from the JSON into a request object, And then we call process, which is going to be just the construct the email and send it. All right, let's run this one. All right, what is our, so you can see that the topic name is demo.customer requests. What is our message this time? From Rob to the Rob at robrichnot.org. Please have plenty of hair conditioner available. Can't imagine why. All right, you're looking a little red there, Rob. I'm not sure. All right. Anyway, so let's send this request in. And so this is now pushing that out to Kafka. And you can see here we sent this and pushed this into offset 5 on partition 1 with no headers. And here is the actual value of the message that we sent, of the, that we pushed into Kafka. And then of course we retrieved that same message and used that to send an email. And there's our third email. Any questions on that? So Kafka streaming. This one's interesting. Like CDC, we are able to persist quickly. It's very easy to scale and very easy to fan out. In fact, the scale and fan out patterns for that are almost identical to that of Cosmos DB for CDC. You just create a new consumer group to get to fan out into multiple, to be able to do different things from the same set of messages, so from a repeated set of messages. And you could just spin up a new consumer with the same group ID so that it doubles your capacity. Each time you're adding the capability to do more, to handle the throughput, to handle the messages faster. This one, of course, captures every update. Kafka is fully from the log, and it pushes every message out to you. So if you need every message, Kafka is a better solution. Almost all, in fact, I think all of the reliable messaging clients are that way. So if you're using RabbitMQ or what have you, again, you will have these same benefits. The interesting thing about Kafka in this one is you could actually think about Kafka as also an implementation of the CDC pattern, because Kafka is actually based on the log, but in the same way that the databases are based on the log. So they talk about Kafka as being a database turned inside out. You can query Kafka like you can a database, but what is generally presented is the log view of Kafka, and the queryable view kind of takes a back seat. Where with databases, or most traditional databases, what you get is that queryable state view, and the log takes a back seat. So it's interesting that, at least with Kafka, you're using a streaming pattern, but you really could see it, and it's almost identical to the CDC pattern for a database. Now, the difference here is that poison messages can be very difficult to handle in Kafka, because Kafka is I've forgotten the word. Wow. But you cannot change things once they go into Kafka. They will stay there until the time to live has expired in there. And there's nothing you can, well, I shouldn't say nothing you can do, but you have to take extreme action to get it out of there, which means that every client, every time it needs to read that message, is going to have to deal with that poison message. So one of the things you really want to be careful about with Kafka is not getting that poison message in there. Other types of reliable messaging services like RabbitMQ or Service Bus have their own foibles, but they are easier to get rid of poison messages in general. So, And again, we are still susceptible to errors on commit. We still have to commit the fact that we have successfully read and processed this message. So we can send the email, have an error on commit, and still end up having to send that email again because the commit failed. All right. So you notice that all of these patterns are very, very similar. They're doing basically the same things. They're persisting the data first, then acting on it. CDC and streaming make it really easy to fan out and to scale. Outbox and streaming guarantee that all the changes will be sent, whereas the CDC pattern doesn't necessarily. But all patterns are susceptible to errors at the commit time. So what can we do about that? Is there anything we can do to avoid those commit errors? Well, in general, the answer is no, but there are some things that we can do to reduce the impact of them, or to be able to not care. The fact is that these patterns will get you fairly close. I said very close here. I'm backing off that a little bit. These patterns get you pretty close to 4 nines of reliability, at least within this service, because what we're doing is just effectively those two things, right? We do the action we need to do and then commit it, period. We're not doing any more. So as long as our dependencies are reliable, at least 4 nines, and as long as our network connections are reliable, at least 4 nines, we're going to get pretty close to 4 nines of reliability. So maybe this is good enough, but maybe it's not. Another important feature of this is all of them, if there is a commit error, it will always fail the same way. It will always fail by duplicating the action. So if our actions are idempotent, then we don't care that we had an error on the commit because it's an idempotent action. So idempotence is critical. If there is any reasonable way without causing other reliability problems to make your activities idempotent, you should do that. That said, that's not always going to be possible. And there may really be circumstances where you need to guarantee that it doesn't get repeated, or that you get exactly once delivery. Exactly once delivery is possible. Well, maybe not in that name. Exactly once is maybe a little bit of a misnomer. But exactly once in the context of 4 nines may very well be possible. There is an implementation of that uses exactly once delivery that uses Kafka, that basically depends on having idempotent ingress. So basically Kafka will recognize, assuming you give it the same key every time, Kafka will recognize that you've sent it a duplicate message, and it'll ignore it if it is a true duplicate. So now Kafka only has one copy of that message. And then your downstream consumer needs to commit to the database a state change, and within a transaction, also the offsets and other information needed to know I got this message. So basically every time it needs to go and fetch a message, it says, where am I? Oh, the last time I successfully committed a message here, it was from this offset. So I can use that to get the next one. That's their implementation of exactly once. And that's pretty limited it feels to me like there are going to be few use cases where that's really both valuable and doable even. You have to have a database where you can make an atomic write, but you can't do anything else in that circumstance. And then anything else you do downstream is going to be dependent. You're going to have the same problem. So unless you're specifically just updating a database that has transactions, unless that's the goal. Maybe you can make some transformations in between or something like that, or go and augment data. We'll talk a little bit about data augmentation here in a few minutes. There's really very little you can do using exactly once delivery. So I don't recommend it for most things. That said, if you really need it, know it's there, know it is at least conceivable that it could work for you. The key though is idempotence. Is if you can make everything idempotent, you're going to be gold. And that's not trivial to do. All right. So there's one more family of patterns I want to talk about tonight. And that kind of allows us to tie this all together a little bit. And that's the saga pattern. There are two different ways to implement sagas, with an orchestration or with a choreography. And the whole idea of this is to allow us to coordinate multiple actions. So if we have it using an orchestration, basically what we have is a controller that is responsible for coordinating all the actions of the participants in the saga. So, the thing for me about this is that because you have that single point of failure, I feel like something like Kafka is almost a requirement for a saga orchestration. Because if that orchestrator goes down, if that coordinator goes down, it has to be able to get back to its exact state where it was. So somehow you have to persist that state. And it doesn't feel to me like a typical database would be really good for that. Feels like something like Kafka would be better for that. But then there's also a choreography where there isn't a single thing, but it's where those could be a little bit harder to change down the road when you want to change the how the system works. But that's where each service does its thing based on upstream events and then appropriately publishes downstream events that other services respond to. So here's an example of an orchestration. It might look something like this. The first two items here are the same two items that we've been doing all day. We write to a database and we send an email. I've also added in here, we call billing and we actually call the request action service, which is the thing that actually guarantees that we satisfy the customer's request. Now you'll notice that each of these has an inbound queue and an outbound queue for errors. So what this is doing is it's saying, all right, do the thing. If it fails to do the thing, it can roll back. But if it has an error doing the thing that it can't recover from, it can push a message back into the update, into the error update that then is responded to by the orchestration service, and it will take additional action. So for example, if there is, if we need to undo the billing, like the request action service gets an error and says, we can't satisfy this request. Well, we've already sent the billing off, so what are we going to do? Well, the orchestration service can say, well, send a reversing transaction for that billing. Pretty common pattern there. This is a good way of doing things, but it's not my favorite. My favorite is Saga choreography. And this to me uses it's like a hybrid approach, and it takes advantage of the best features of, CDC and streaming to implement what I call the microservices pattern. We went a long way to get to that microservices thing. But to me, this is actually what represents microservices. They're doing one and only one thing, plus committing it. They manage their own data as much as possible. And they're very independent actions. So let's follow this through, for example. In this case, we've got a user that issues our request to the request API. The request API just pushes that into, in this case, Cosmos, and response to the user says, I got it, fam, you're good. Then we use the CDC pattern and fan out to two different things here. First, our email responder, which then sends out the email that says your request will be processed, and this billing data augmenter. Now, we haven't talked about data augmentation much in this talk, but that's its own pattern, but it's really useful. In this case, what we're doing is we get that customer information, and then we're going to pull in some additional information from the CRM, from our customer relationship manager, and augment that data and throw that into this billings queue here. And then the billings service can use that. Now, in a lot of traditional architectures, this would all be done right here in the billing service. But you notice I have the danger triangle in here in the billing service already. Can you see why I have that danger triangle in there? Everybody's muted, so I'll just answer the question.
We're billing whether we send the email or not.
That's true. I don't know if a confirmation email would be a problem. What was the other answer there?
Talks to the external system bank.
Yeah, I mean, ultimately what it's doing is it's got already two writes in here. It's got a write to the external system, as you said, as well as update, push a new message out here to this, a success message out to the successful billings topic, as well as committing the message it read off of this topic. So we're already doing two things here. And in this case, we really can't avoid it because we have to send a downstream message. So this is the only thing I really don't like about this type of pattern, is that we sometimes still have to do two writes, but we can avoid doing three using this augmentation pattern. And probably most importantly of all is that in many, many architectures, everything in here is all done right here in the user request service, where this request service in many architectures updates the database and sends out the email response and calls the billing service and does all of these things. So what we've done is we've broken this out into an actual microservices architecture. And that is my definition of a microservice, that it basically does the minimum. It does one thing. It makes one change to system state, or as close to one as humanly possible. And this is what's going to give us reliability. We're going to be able to tell if any of these fail. We're going to be able to tell exactly what failed and exactly how they failed. And we'll be able to fix them, and we'll probably be able to fix them using these existing tools. If the email doesn't get sent, we could just call this email responder to send it. If the billing doesn't get done, we can call the billing. Well, that billing may be a little bit different because of the fact that it's got two things that it's got to do. So we'll have to be careful there. But that's another thing here, is that in the places where we're doing two things, it's easy to call that out. So it's not perfect. But this is going to be a lot more reliable, certainly, than putting all of that in the user request API like we tend to do today.
Do we have two different hooks to Cosmos's CDC? Or is Cosmos CDC calling something that then simultaneously calls those other two things?
Well, we're using the it's just like it was in the sample code. So we're using the what do they call it? The change feed, the Cosmos change feed handler, and we just tell Cosmos, I am an instance of this group, and it handles managing however many consumers you have for that group and however many different groups you have, and it manages all that. It actually creates a container specifically for managing all of that. It creates what they call a leases container. And we can actually look in the containers and see this lease is managing these consumers and all, and everything. And if one of the consumers goes down, it'll automatically rebalance it for you. Kafka does the same thing. So it handles a lot of the details of this for us. So we don't have to worry so much about it.
That's beautiful. It avoids the double write problem too, because otherwise, as that forked, you'd have exactly the same double write that you have in the billing service.
Yep. Exactly. So in this case, we don't have to do any of that because the only thing we're doing is updating this. We're reading here, but of course, reading is an idempotent operation. So if we read and it fails to write to billings, so what? We'll read again the next time when we retry. And these services are all built that way, right? So that if we fail to do something, it throws up an exception, and we retry. Now, of course, that could be dangerous too, because if it is something that is not a transient error, we have to manage that. So if, for example, we get a message that simply cannot be, it is just badly formatted, there's no way we can read it, or it's something to there's just no way we're going to be able to handle that, we have to build that into it. Generally, we can throw it over into a dead letter queue or something like that. We could log it and ignore it. There's lots of ways to handle it. So we have to take that into account. But we don't have to worry about scaling. We don't have to worry about fan out. It'll manage all that for us.
The reading is idempotent, but really we're not doing a reading, we're doing a saga. We're doing the reading and the merging the data together and the writing to the billing queue.
Right, but the only change to system state is the writing to the billing queue. So the only thing that could get repeated if we were to blow up in the middle of it, or if we were to do it and then fail before committing, the only thing that's going to get repeated that we care about is the writing to here. I don't care how many times I read from this database.
Oh, good call. And if I have a mechanism inside that billing queue to avoid duplicates, then I can create an exactly once write scenario.
Yep, absolutely.
Perfect.
Yep. So to do that, though, we'd have to have an ID, a key to send into here that is going to be the same every time, no matter what. So, which is very doable in this case, because we could be like the customer ID, for example, or something like that. And as long as we're always guaranteed to use that same key, then Kafka will even manage that idempotence for us.
Well, I would say probably not the customer ID, because that presumes that I would only charge the customer exactly one time ever. I would say the request ID, though, either the request ID from the request database or the trace ID from the user request API.
It could be composite also. It could be customer ID, sale ID, for example, composited, something like that. But yeah, you're right. You are correct that we would not want to only allow a single message in the queue from only one message per customer. That would be bad. So yeah.
Yeah, this is cool. You've made it much more reliable by leaning on each of these patterns and stitching them together nicely.
I think so. All right. So I just talked about how in a lot of cases we end up throwing all that stuff in here. And how I broke out this here. It might be the simplest thing. People are going to look at it and say, hey, we've already got this method running. We've already got this trigger. We're already doing work at the time we need to do it. So why don't we just add on? We could just, we're already got the email responder and we need to call the billing service. Why don't we just do that work here? And my big takeaway for you is don't add on inside an execution context. By doing that, you are destroying your reliability. You're making it hard. You're sacrificing your nights and weekends. Don't do that to yourself. If you're a project manager, don't do that to your team.
The execution context here is just inside a single signal or trigger of a request.
That's
so
right.
Like the same deployable, like all of those components could be in the same deployable. It's just
Yes,
breaking it out so the signals are separate.
correct. Thank you for pointing that out. You're right. It has nothing to do with the container. So we can have 10 different web methods inside a single API, but we're talking about an invocation of a single web method here. You can put as many different web methods in the same API as you want. I could go for a drinking game where every time I say item this. All right, let's sum up here so we can get to the drinking portion of this program. All right, so in summary, it is impossible to reliably take two actions in a single context, single execution context. I know I haven't proven that to you yet. It's very difficult to prove a negative. Know that I believe this to be true. And as you play with it, if you ever find something where it is actually possible to do that reliably within a single context, please let me know. No, you don't get to see a Saga implementation demo. It would just be too complicated to, but I would love to see you do a pull request on that repo that actually uses all these toys and uses a Saga and creates a Saga demo. I would love to see that. All right, so like I said, I know I haven't proven it 100%. I definitely believe it to be true, and if you find something that it's not, please let me know. But I definitely do my work based on this principle, and so I will always try to avoid doing more than one thing at a time. I've said it over and over again. Aside from idempotent, I also said persist immediately, get it to disk fast, get it safe on disk, then do other things downstream, especially if it's data coming from a customer, or if it's expensive data, or anything like that. Get it to disk, get it safe, and then worry about everything else. Outbox, CDC, and streaming are all patterns that will help you keep those operations separate. There are ways of avoiding having to cram them all in and add in as you can avoid that. You don't need to do that, and you're going to be happy you did that. I tend to prefer CDC or streaming because they are better for fan out and scalability. That said, Outbox is a perfectly valid pattern for many use cases, and I don't want to suggest it isn't. But I prefer CDC or streaming whenever I can. Think about your sagas. Think about how you can either orchestrate or choreograph these complex interactions and do so in a way that makes it easy to identify errors when they occur and to remediate them when something happens with the data. So you know, here's what happened, here's what failed, and here's what I need to do to fix it. And then never, never, never add on. Do not fall victim to that temptation. It's easy and it's dangerous, and it will eventually hurt you. And the more your systems scale, the more at risk you are. And of course, that also means the heavier your load at any point in time, the more likely you are to have one of these very difficult problems. So these problems show up at the worst possible times. So avoid them when you can. All right. Here
it looks like though we've traded simplicity for reliability. And so if our goal is simplicity, then moving in the other direction, but having a less reliable system might be a decent trade-off. On the other hand, if reliability is the key goal, then sacrificing simplicity to get there is definitely an adequate solution.
I hear
Does
that kind of
right?
thing a lot. I do. To me, a system that has all of this crammed into here is not simpler than a service that does this, and a service that does this, and a service that does this. Those are really easy for me to understand. And we have good tools to map these kind of dependency chains now. You almost get this for free in Azure, almost with App Insights, where you can see exactly what's communicating with what and when. And there's plenty of other tools around that allow you to do that kind of thing. You do want to do things that are some best practices. Like it's always a good idea to have a correlation ID pass throughout the system, so that you can see that this change caused this change, caused this change, that kind of thing. But for the most part, I find it a lot easier to deal with this kind of system than with the big ball of mud.
I agree. In the big ball of mud, though, we only have half the boxes. It's one big exe and it's difficult to trace through, but we do have less moving parts.
Why are you trying to? My number one thing in my job is drawing pictures. Why are you trying to take my job away from me?
Oh,
like
well then
drawing
this
pictures.
is so much better. Check out all of the PowerPoints we've got.
Look at these cool boxes and arrows and things. Even got
Yeah, it
colors.
is really sweet, and it did solve a really difficult problem in a really elegant way.
So here are some resources. First off, the most important one, you click on that and you can go to the Carvana jobs website and fill out some applications and come work with us, and you'll be happy you did. This is a link to the GitHub repo with all the code samples. Some articles on idempotence. You're going to get drunk now. As well as the other patterns. Some stuff on different tools for data streaming and the Saga pattern. And then this one, it's actually, there's something else down there. I think that it's, it hit it off my screen. Terrible. It wasn't doing that earlier. Oh, that's because this is in the way. Why was it? Earlier it was auto hiding my taskbar and it's not doing it now. Oh well.
Switch tabs and switch back, and it'll hide your toolbar.
You liar. All right, no worries. I'll figure out what that's saying. Oh, it's this is a link to the plant UML diagram tool. So that's the thing that I use to view the sequence diagrams. So you'll need that if you want to see the pretty pictures of the sequence diagrams, or you can always take it out and plug it into something like websequencediagrams.com or something like that to see them. And then this one is really interesting. This is an explanation of the SQL Azure service level agreements. And this is where it talks about why service level agreements are done based on time and not based on per transaction, per action types of things, and why that makes sense. And it also is the explanation at that point then for why transactions don't improve reliability. They can only improve data integrity. So this is an interesting, if boring, read. Is that possible for something to be both interesting and boring? I don't know. Anyways, that's all these resources. You can get all those resources by going to this URL. And I'll put it in the chat this time, Rob. Yeah, that should be an HTTPS. See if I got it right.
No, you spelled it wrong.
Avoiding dual rights.azure websites.net. No, I did it
You
right.
spelled it right in the slide, but you pasted in the wrong text.
No. Oh, the one Rob did. The one I did is just fine.
Oh.
Oh, you're correct. I transposed the I and the O. Whoops.
Just a couple more things I'm going to show you in here. I have a couple of appendices in here because I'm just that retentive. Uh, I've got a slide in here that talks about uptime metrics. So what 3 nines mean, 4 nines and 5 nines. So it's there if you want it, as well as delivery guarantees, at least once, at most once, and exactly once. So what those mean in general terms. So those are there if you want them. So I'm happy to answer any questions. We did go a little past 8, so probably shut it down pretty soon, but I am happy to answer any questions that you have. And thank you for paying attention.
This was really awesome. Well done, Barry.
Thank you, sir.
And I have a question about, like, we talked about 2 dual writes and how to be making it reliable, but there is also like a concept of like eventual consistency.
Mm-hmm.
So is that like your retry patterns have to get mixed up to make it eventually consistent?
No, I think what you're going to actually find is that all of these patterns really result in eventual consistency. Now, of course, it depends on what you're thinking about as in terms of consistency. But just as an example, this Cosmos update, this Cosmos database will not always be up to date with this accounting database, right? Because it's going to take time for this to flow through. So this may not even know about a change here for a while yet until the billing has been done. So, you know, this kind of system is eventually consistent. And that's a good thing. I think we live in an eventually consistent world. The speed of light is not infinite. So there is no way to actually have causation at the exact same time as the reactions to things. So we should embrace the fact that our world is eventually consistent and make our data eventually consistent and expect our data to be eventually consistent.
So in the example of the microservice with the Saga pattern, like, so how would a user handle to a situation if one of the things fail, right? So in that case, like, the Saga orchestrator or something has to roll back the whole transaction, right? Or would it kind of like retry that? Like, can you talk a little bit more about an error situation where one fails, and like how would the system correct itself to get into a consistent state?
So in these cases, it generally you usually use these kind of patterns because you can't just do a rollback. The usual pattern is either to issue an offsetting transaction, like for example, if I talked about in this one earlier, if we have billed the customer for the request already, but then it turns out we can't do it for some reason and we need to refund their money, we say, oh, well, we got an error here, and then the orchestration service is responsible for issuing a reversing transaction here that's a credit instead of a debit to their account. And that's pretty typical for these kinds of sagas. I don't know, Nate, can you think of any other things offhand where there's examples of how to handle these kinds of errors in an orchestration scenario?
I mean, there's other transactional consistency patterns like a routing receipt and a few others, but like you're effectively going to have to issue a compensating transaction at some point.
Did that answer the question?
Yes. So from the user request API perspective, so that transaction would be a failed, or it would have not processed successfully, right? So there has to be something like the user has to process the request by initiating again.
Yes, we probably have to have something down here as well that says, okay, if that occurs, the orchestrator will also send a signal to this other service down here. Maybe it's to the email responder service or something like that, that then notifies the customer, sorry, we were not able to handle your request. Something like that. Yeah. So you're right, it's going to have to take care of all of the details of it, not just, you know, reversing that one transaction, but also making sure that based on the state of the system, everything does, and everything ends up in the state it should be, it should end up in based on all of the activities so far.
Okay. Yeah, what I was thinking was, even with the individual billing service or the microservice, even if it fails, there is a exponential back off and it kind of retries before it kind of goes back to the orchestration service to trigger an offsetting transaction or something like that. So probably those probably is in the details of the box inside the billing service.
Yeah, I imagine so. So certainly the retries would be there. Yeah, it's hard to know with, you know, especially with banks. Who knows what their APIs look like? A lot of them are still on mainframes, right? So
Yeah, so that's exactly the point why I picked billing service as an example. So we get to talk about that.
yep, exactly right.
And
Yeah,
that's where Saga orchestration versus Saga choreography is so interesting, because in choreography, you may have more clues about where you left off and where you can pick up to continue on or reverse. Where with orchestration, it's really easy to do multiple tasks in the same process, or to lose context, to lose state of, you know, which step you're on.
I'm not sure I fully followed that.
In choreography, one thing is going to kick off the next thing, and that thing's going to kick off the next thing. And so it's easier to find where the train ran off the tracks because this thing happened, but that thing didn't. With orchestration, there's one piece that's doing all the things. So maybe at the end of the data updates, for example, or update errors rather, it writes back to the orchestration service and says, I'm done. But it's really easy to just do all of the things in sequence. And now we're back to the multiple write problem.
Yeah, and how to deal with that is not a simple problem either, because you could end up, right, you know, exactly. I think this is actually what you're saying. If, for example, I try to give myself a topic out here that every time I do something, basically as an orchestrator, I write it out here as well, so that I always have a log of exactly where I'm at and what I've done. Then you're right. Then we're back in. We've got another write. We've got dual writes for all of them. It would be easier if we don't have to do that. If we could just, oh, I got this signal, that means I issue this signal. So we could just make it kind of a state machine kind of a thing and say, under these circumstances, I've got this signal, I do this. Actually, not a state machine, because state machine would require maintaining state, and we don't want that. I got this signal. That was an error in the billing, so I know I have to do this thing. Or I got this signal that says an error in the request action that I was unable to complete, so I have to update, I have to send this thing to billing, and I have to trigger another action for what do you call it, letting the customer know. And I have to be very careful about how I do that, because you want two different signals for that, because you don't want to do dual writes for those. So you end up having to have two consumers here managing that. So it can get a little complicated.
And because you're doing all of those things in one orchestrator, you've kind of built yourself a monolith, and that's awkward too. A state machine is a simpler mechanism to solve that problem, but now you have state, and yeah, that's even more fragile, because now you have the double writes at each step. You have to do the thing, and you have to update the state in the state machine.
Right. Yep. And you can end up with, I did my thing, but I had an error when I was updating my state, so now I'm all disconnected that way as well. Yep. And you know, like I said, none of these patterns are going to be perfect. So it's very use case dependent, and we just have to be aware of it. We have to try to avoid it whenever we can. Never allow yourself to do more than one thing at a time. But we're never going to completely eliminate, at least I don't think we're ever going to completely eliminate dual rights completely. You know, it's just not there. It's not a reasonable thing to expect it to be an absolute. We just do the best we can.
And the other take-home message is don't try to send email. Just post it to Slack. It'll
Yeah,
save yourself a whole lot of headache. And then you can have more idempotent transactions.
I don't know. Is Slack idempotent?
No, but that was funny.
Okay, fair enough.
So why don't you give an example of WhatsApp and delete message, send out a message and delete for everyone?
I didn't catch that. I'm sorry.
No, if not Slack, use WhatsApp or send out a message and use the feature of delete for everyone, and so that you send out a rollback of that transaction.
I see. Okay. Yeah, we actually did, you know, have email rollbacks at one time, right? Where there was supposedly you could like what was it? You could request a
Delete unread message.
yeah, there was something. I can't even remember what it was. It never worked though. So oh
Yeah,
you
the
could request
RNC
a
learned how
recall.
that request retraction doesn't work so well.
Yeah, it doesn't work at all.
I'm intrigued by the WhatsApp solution though. You know, if I post it to WhatsApp, then maybe I could say, Alexa, buy me a dollhouse.
I before I started this presentation, I actually hit the mute button on my device so that because I knew you guys would try and say something like that. So my device has been muted this whole time.
Cortana, delete all contacts.
Is there such thing anymore? They crippled all mine. My Harman Kardon Invoke no longer is a smart speaker. Now it's just a Bluetooth speaker. That was crushing for me. My phone, I have to use the Alexa app on it now instead of Cortana. Just killed me.
You have to use your hands? That's a baby's toy.
I don't use my hands. No.
And are there tools or patterns you avoid or see? Like, I was thinking, like, if there are like events and Kafka listeners that wouldn't be easily possible to you to run into a cyclic reference or infinite loop, or are there tools or things that detect that and stop you from doing that?
There's a couple of ways that you can configure the consumer in Kafka. You can say, I would like to commit and then do my work, or do my work and then commit. And depending on how you choose to configure that consumer, you may run into interesting problems. Barry talked about the dead letter, the poison message concern. If I have a mechanism in Kafka where I choose to do my work and then commit, and I have a poison message, some message that I can't process successfully, my system just throws an exception, I'm just going to keep retrying that message and throwing exceptions infinitely. On the other hand, if I choose to commit my message and then do my work, it's possible that if I throw that exception, then I don't know. You know, I've already processed that message. So a mechanism to avoid that is to have a dead letter queue where I can pull the message, try to execute it. If it succeeds, I do the work. If it fails, I may retry it a couple of times or have Kafka pass it to me again. But if I've tried to process it a bunch of times and still fail, copy that message into a dead letter queue and then move on.
Well, at that point, there's a couple of issues there, though, especially with Kafka. First of all you could do is commit it and say, I've read it with Kafka. You can't pull it off because it's Kafka. There's no way.
Yeah, exactly. So everybody reading is going to have to take that action as well.
Yep. And then the other thing is, as soon as you go to like a dead letter queue, your order is blown. So if order is important to you, you really can't use a dead letter queue that type of pattern. So that's only really good for things where order doesn't matter.
Right. So if you have an atomic experience where, I need to send emails and here's all the emails I need to send, doesn't matter in what order I send them. I just need to send all of them. If I'm updating bank balances though, yeah, that's really important. And I need to be able to do them in sequence, because if the moment that I update the balance and then update it back, I'm going to get the wrong answer, much like YouTube view counts. They kind of go up and down for a while. Yeah, this was really amazing. Thanks for speaking today, Barry. You did a great job.
Well, thank you.